cast out there was only one frame and then sound for the entire lecture, then I decided to make this short version just as a screencast. So just so that you have a little bit more information than just sound. Okay, so today we'll cover stochastic processes. We'll look into so-called moving average, autoregressive models, combined also as armor models. We will talk about non-stationary models, how to make them stationary, and finally a little bit about prediction. So what is a stochastic process in general? It's a function of time and the realization omega. Time is a member of some index set. Likewise, the realization is also some sample space. Now, what can we do in practice with all this? This is a little bit more abstract than what we have done, but if we look at a particular point in time, this means that we have a realization, it's just one outcome, but in general we have a sample space. So we have a random variable with some density of some kind. Now, for a single realization, if we have just omega, then we have a time series, which is what we usually have, and when we observe it, we have it as xt. Now, as here, we will focus on discrete time things here, and we will also focus on realization living on the real numbers. As an example, just to illustrate what was on before, here is a stochastic process where we have three different realizations called omega 1, 2, and 3. If we look at a particular point in time, then you can imagine if you have all the distribution here, then you could have, say, a normal distribution as a cross section here, sort of like this. So that's the idea. So what we end up with is an n-dimensional probability density function like this, where we have at n chosen time points, then we pick the n's and we can pick them any point in time. Usually what we will do is to have them at equidistant point in time. So what we call this is the finite dimensional probability density function for the process. Finite dimensional because we let n be finite. And it does completely characterize a stochastic process in this case. So, particularly when we're in this discrete case. So the mean of a stochastic process, well, that's the same as the mean of any other stochastic variable. We take the integral over the outcome, multiply by the density, and integrate over the sample space, which is R. To do the second order moment representation, we also need the autocovariance, which includes the variance. And the definition here is similar to what you've seen before. It's a covariance between x and not y, but x at two different time points. We can write it in this way, or we can subtract the mean value at the corresponding times. The main thing here to notice is the definition is not covariance, but it's the autocovariance. We use the covariance sign here, but we call it the autocovariance. Auto means with self, so it's the covariance with yourself at different points in time. And as usually, if you take the autocovariance at the same time, then you get the variance with the usual definition down here. Okay, so the next thing is stationarity. A process X is strongly stationary if all finite dimensional distribution functions are invariant for changes in time. That means for every n and every subset and for any shift in time h, it holds that the reference density here is the same as when you shift time h. If we go back to the slide here, it means that the distribution here is the same as the distribution here. If that is the case, that is strongly stationary. The full distribution has to be the same, not just at one point, but if you shift the time, it should be the same. We can also have so-called weakly stationary processes of order k, where the first k moments are invariant change in time. We will typically just look at weakly stationarity of order 2, meaning that the mean and the covariance are invariant changes in time. We will also call that just to be stationary. So we have a fixed mu for the entire series, and we have a fixed sigma square as a variance across the entire series. And the covariance, autocovariance, only depends on the time difference, not on the actual time point. We'll get back to that a little bit later. So this is what we have, and since we will generally deal with noise that is Gaussian, and we will have sums of Gaussians, we are still in the Gaussian range, and if we know the mean value and the variance, covariance matrix, then we fully describe the system. So whenever that is the case, the weakly stationary order 2 implies strong stationarity, but only when they have normal or Gaussian processes. Another concept which we will not dig so much into, but just so you have it as reference, is ergodicity. So we normally assume that we have access to only one realization of the process. But what we want to say something about is the entire process, not just the realization, but we want to say something about the random variable xt. What we typically do is we require that a process is so-called mean ergodic, which, if you look at the first part as in stopping here, we have the expectation of xt is the integral of x over the sample space. This is the usual definition. If the process is mean ergodic, that equals, for the limit, the integral of x of t comma omega for the particular realization that we're looking at, normalized by 2t as in the width of the integral. So what we have here is just the mean value of an interval of time of the particular realization that we have. So if this is true, then the process is mean ergodic. So basically, the mean of the ensemble here equals the mean over time. And if you want to have more examples, you can have a look at this webpage. So what we will focus on are some different processes. We look at normal processes, also called Gaussian. I will also swap the word a little bit just to keep both active. So there, all finite dimensional distribution functions are multivariate normal distributions. We will also focus on the Markov property, where the conditional distribution only depends on the latest state of the process. So if I'm at some point here, then moving around somehow, the prediction of where I'm going to be, all the information about that is in the current state of the process. That is what is set down here. The probability density function is, if you condition on all previous observation, if that is equal to only conditioning on the latest observation, then the process is Markov. We also have deterministic process. You've heard a lot about that in other courses. Basically, you can predict without uncertainty, just given some past observations. And you have pure stochastic processes. That's what we'll focus more on. They can be written as potentially infinite linear combinations of uncorrelated variables. And you can also have combinations, well, sum of a stochastic and a deterministic process. So we can decompose any process into these two different parts. As said, I will get back to the autocovariance function. Here I've written for stationary processes, it only depends on the difference in time. So if you have a process and you look at the difference here and you shift the time, well, it's the time difference that matters because the distribution function is invariant to changes in time. So therefore, we can always change the time to get whatever offset that we like. The definition is thus the covariance of xt comma xt plus tau, which is the time difference. If the mean value is 0, it reduces to this. Otherwise, each term has to have subtracted the global mean value. But we will often this cause, without loss of generality, assume that the mean value is 0, just because it makes a lot of calculations much easier. You go from covariance to correlation the same way you do from autocovariance to autocorrelation, by taking the covariance at some particular lag in this place and normalize it by the variance. So it's the usual definition. A couple of helpful properties is that the autocovariance of tau equals the autocovariance of minus tau. So taking and going forward in time is the same as going backwards in time. It's the time difference that matters, because if the covariance is the same between 2 points, well, you know from a variance matrix, a covariance matrix of a normal vector, you can transpose that and a symmetric matrix, which also means that going forward and backward in time is the same. Another thing is that the absolute value of gamma of tau is always less than or equal to gamma of 0. The easy way to say that that has to be true is if, say, gamma of tau is greater than gamma of 0, which is the variance, well, then the correlation would be greater than 1, which per definition is not. So that is the intuitive reason why that works. So moving on to linear processes. A linear process can be written on the following form. We can have a mean value which we can subtract from the entire sequence, and then we have something that does not have a mean value. So if we define this xt equals to this, we would have something where the mean value was 0. And then we have written it here as an infinite sum of epsilons previous from time t down to t minus infinity, with some weights on here, some size. And we can scale, there's two ways we can scale this. We can either scale sigma epsilon here, that gives us the epsilon, or we can somehow make a constraint on the size. What we will do generally is to say that we will scale the epsilon such that the size 0 weight equals to 1. Okay, so the psi and pi weights. If we go back here, what we look at here is the time-shifted epsilons. That's quite similar to what we did last week when we used the backshift operator as a polynomial of a similar form. If we define it like this, we have a 1 corresponding to psi 0 equal to 1, and then we have for I equal 1 to infinity, the psi weight and b to the I power. So this here is equivalent to the expression that we had on the previous slide, with the exception that here I assumed that mu is 0. Okay, so this is the definition from before of the linear process. If we can invert this polynomial, as in if the inverse operator exists, then we can also write it, well, the form looks the same, but we call them the pi weights when we have them acting, this operator acting on yt instead of acting on epsilon t. Now, this is one of the things that is easy to see if you do it on a blackboard, but let's just try to do it from here. If you use the autocovariance and you want to calculate that using psi weights. So we have it, the system written on this form. It's an infinite sum of weighted previous epsilons. Then we have to calculate the covariance of the process and the process shifted k time steps forward. What you have to keep in mind is now that these epsilons are assumed to be IID, so that means the only place you get a contribution from this infinite sum is when the index of the epsilon is the same. So all the epsilon t plus k does not give any contribution as long as I is less than k. So we need to get down to k here before, then we'd have an epsilon t here, and we have the epsilon t here as well. So we have the epsilon t with psi 0 as a weight, and we have the epsilon t here with psi t plus k as weight. So, psi k as weight. Likewise for epsilon t minus 1, we will also have it here as with weight psi 1, and over here with psi k plus 1. So we'll always have psi's that are k apart, and we will multiply them, and they are all having the same variance, sigma epsilon squared. So that's how we get to this. Stationarity, well, we defined it before. What is it to be stable? Well, stationary is that the mean and covariance structure does not depend on shifts in time. Now that we have this kind of process, we can do it slightly differently. If we look at this polynomial here and evaluate it for z, then if this converges for z greater than 1, then it is stationary. That is basically saying that the old epsilons are downweighted sufficiently fast. Similarly, a process when we have it on this form, well, it will be invertible if that polynomial here, the pi polynomial of z, converges for z greater than 1. In practice, we will try not to use the infinite polynomials, but try to do something where we would restrain ourselves a little bit to make life easier, but we'll get back to that. These are the, you can say, the traditional definitions. So in practice, what we will have is a limited number of observations. So typically, let's just say n observations here, and our task is that we need to find an infinite number of parameters, as in the psi 1 plus psi 2, and so forth, given n observations. That is not something that we want to do, because then we'll have an infinite number of ways to do that. And generally, we prefer to estimate parameters when we have, you can say, more information that is what is needed. So we need to find a way to restrict the sequence more than just saying that the first number is 1. We still have an infinite sequence. The way that we will do that is by defining the classes of moving average models, autoregressive models, and combined autoregressive moving average P, Q models. So the moving average model is a model where the YT is an average, a weighted average of previous epsilons. The autoregressive means regression on yourself. Well, we have YT, we have, it depends on YT minus 1 down to YT minus P equals to epsilon T. And of course, you can combine these two and get what we call an armor P, Q process, assuming that epsilon T is white noise. We can also write this in operator form from this up here to that one there. Say, so this gives us theta of b equals to 1 plus theta 1b plus blah, 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 plus theta q b to the q power. So that's the theta polynomial. Likewise for the phi polynomial. And the AMA model is like this. We defined the backward shift operator last week, so I won't say more about that right now. So regarding stationarity and invertibility of these classes of models, the moving average model is always stationary. Whenever you take the average of some values, it is always going to be stationary because it's a sum of finite sequence of numbers. It is invertible if the roots in Z inverse equal to 0 are all inside the unit circle. Note that before we looked at Z, and then it should be outside the unit circle. So this is just flipping between inside and inverting to be, flipping outside to be inside. For the autoregressive process, it's just the reverse. It's always invertible because it's on that form. It's stationary if the roots in the psi 5 polynomial set inverse equals 0 with respect to set all lie within the unit circle. And for the ARMA process, well, it's stationary if the AR part is stationary, and it's invertible if the moving average part is invertible. So that's the definition. And if you've been at the live lecture, you could here see a little bit more examples. So if we look at the autocorrelation, then for say a moving average model of order 2, we can write it like this. Then you will see that the autocorrelation is equal to 0 when you get above 2. Well, how can we see that easily? If we look at this as epsilon t minus 1, epsilon t minus 2, have that sequence here of those three, then at lag 0 you have the same. When you then change the lag to go for correlation or covariance at lag 1, then you have contribution from these two epsilons because they are overlapping. If you go to lag 2, you have these two have one epsilon left still overlapping, but when you shift time more than 2 steps away, there are no epsilons overlapping, and thus there's no correlation. So that's the, you can say, motivation for this. For the autoregressive model of order 1, well, the model is yt equal to 0.8 times yt minus 1. So what we get is that we get, the start with a unity in lag 0. The correlation with yourself is always per definition 1. So lag 0 is always 1. And then when you go out, you go down to 0.8. You go out to 0.8 square, cube, and so forth to get this exponential decay down here. And if you combine a model to make an ARMA 1,2 model as down here, basically combining these two, what you see is that you have the exponential tail still, but here for the low lags, there is a contribution from the moving average part. We'll get back how to identify this and estimate models based on this kind of information, but today we'll focus on the theoretical properties. Later on we'll look into how to do it based on data. We also have the partial autocorrelation function, which is defined as the, well, if you do partial autocovariance first, it's the covariance between yt and yt minus k, conditioning on all the yt's that are in between t and k. So that means that the partial autocovariance is the same for lag 1 because there's nothing in between, but when you go to lag 2, then you will see that, say, for the autoregressive model here, if you know when you're going to calculate it for lag 2, then you say how much information does yt provide to yt plus 2, given that you know yt plus 1. Well, if you know yt plus 1, then there's no information left from the one that is 2 steps back. So therefore, the AR, you only have these coefficients that are different from 0 for the order of the AR polynomial. But for the moving average part, in this case, you have a damped exponential. You'll get back to that later. And again, the combined model, you'll see kind of a combination of the two patterns from up there. So basically what we get back to when we're going to estimate things is, well, when we have some tails out here, we need to get rid of this. This says there is a moving average part. On the previous slide, there is an AR part. So when we get to it, we say, well, probably you need at least an ARMA 1,1 model, maybe more, but you will figure that out and how to get to that later. Just for completeness, we'll also just define the inverse autocorrelation function. If you have the process as defined previously, phi b on yt equals theta of b on epsilon t, then we have the so-called dual process where we flip the polynomials and then we define a new process set t following this process here. And then if you take the autocorrelation of this, then it's providing a similar information as the partial autocorrelation function. So this is just to mention that is here. We will generally restrict ourselves to using the partial autocorrelation function. Okay, so welcome back after this short break. So we will also talk a little bit about non-stationary processes. You can probably easily see that there's one process here that seems to be stationary, and there's another one that is definitely not stationary. So typical types of non-stationarity. One is if you have a long-term trend, in this case a very nice linear trend. You can also have a periodic trend, but you can also have some kind of changes in variance and other structures. This we won't cover in this course. We'll leave that for, say, the advanced time series course or other courses. But we will try to deal with these kinds of patterns in here. So for the trend, what we'll do is that we will not just look at the ARMA, but go for the ARIMA, where we have an integrated part in here. Integrate is the reverse of differentiation. So what we'll do is take the difference of the process, the d order difference, so 1 minus b to the d power, apply that operator on yt, and then get a new process, and then we'll make an ARMA model for that process. So we can also write it in combination as this. So we have the phi b polynomial, then we have the difference operator to the d power, typically d is small. We'll get back to that when we get to look at data on yt, and then we have theta b of epsilon t here, as we had previously. So the main difference, or the only difference, is that we now inserted this difference operator. Considering stationarity, well, assuming that the AR part here is stationary, that will give us some roots inside the unit circle. The nice thing is, to solve this polynomial, well, we can just have to solve each part, each term equals 0, and solving this gives us a 1. So we'll have d roots in 1 coming from this. Also meaning that it's, you can say, the combined process is non-stationary, as we saw it here. It's a non-stationary process, but if we difference this, as in looking at the difference between observations, we'll get something that is stationary. At least that's what we would hope to get. The next layer of complexity is to go to seasonal processes. So we have the ARMA P dq, and now we introduce the uppercase P, uppercase D, uppercase Q with season S. So it's a similar structure as before. We will do the same thing to make an ARMA model, but we won't just do the difference operator, we'll also do a seasonal difference operator that is defined as 1 minus b to the s power. And then we'll do that uppercase D times. So we'll make a model for the, you can say, difference time series. If we then also combine an autoregressive model in the season power, and likewise an autoregressive model in the and moving average in the season, so we have a polynomial here where you have orders of b to the s power. Say you have b to the 12 if you have a monthly, something that happens every year, and then you have b to the 24th power, 26th power, 36th power, and so forth. For stationarity, again, we just look at the autoregressive part here. We have the two autoregressive polynomials, and then we have this one here gives us d, lowercase d roots in 1, and this here, 1 minus z, gives us s roots around the unit circle. And then the inside ones are the ones from the 2, 5 polynomials here. We'll get back to these things in a later lecture. So often what we want to do is to find the case where the two d's are equal to 0, so the process is as such stationary. And just, this is a general case. As an example, we'll look at this here, which is an autoregressive model. And you can say it's an AR12 model with a lot of coefficients that are 0, so it's not a good way to kind of declare it. The nicer way is to say, well, it has season 12, and then it's an AR1. So it's yt depends on yt minus 12 plus epsilon t, as written down here. So it depends on the previous season and the season before that and before that and before that. And if you look at the autocorrelation function from this, we saw before that the AR1 process had an exponential tail. We had the same thing here, except that we have something in lag 0 that is a 1, and then we go to lag 12 for the next one, which equals to phi, and lag 24 we have phi squared, then phi cubed, and so forth, where we move on. You can also have a look at example 510. So the next topic, which is what we will be spending a lot of time on, is how to make predictions. Because now we look at the different processes. We looked a little bit on, well, if you have seasonal models, then you can do seasonal differencing, and somehow we can deal with all that. What we need now have to kind of get starting at is when we're going to estimate models. What we want to do is to minimize the square error, or sum of squared errors. So we want to do the conditional expectation as it is the optimal prediction in that case. Typically we'll use k greater than or equal to 1. In most practical purposes that we will use for estimating things, k will be exactly equal to 1, which is the easy case, but as for the assignment as well, you will be looking sometimes for something that is a much larger horizon than just one step ahead. Okay, to make an example of the prediction, if we take the AR1 model, we can write it on this form, and you should note the sign on phi. Sometime phi will have, you can say, positive sign on the right hand side and sometime on the left hand side. And I will try to also stress that a little bit here and there, but you'll see how that goes. So the one-step prediction is y hat t plus 1 given t is the expectation of y t plus 1 given all the previous y's. So we can insert the expression from up here like this, and the nice thing here is that, well, yt, given that we know yt, that is just yt. And the expectation of epsilon of t plus 1, that's a future epsilon expectation that is 0, and the expectation is a linear operator. So what we get is phi times yt in total. So that was fairly easy. If you do want to do a two-step prediction, well, we do the same thing, except that now when we get to this, we only get to phi times yt plus 1 plus epsilon t plus 2. But we cannot do anything about this right now, except that we could do what we did before to insert what we have up here. So we'll just insert that the expectation that we had from up here. So we insert the estimate and we get phi squared times yt. And if you continue this, you can see the easy recursion is just phi to get y hat t plus k given t, it's equal to phi to the k power yt. So if we do this, what we get is we have some observation, and then at some point at time t, we just predict out into the future. So how likely is this to happen? Well, it's not going to happen that way. We need one more thing. We need to have some uncertainty here, which is expected to increase as time progresses. So let's look into the variance of the prediction error for the AR1 model. First of all, the prediction error of a k-step prediction is the true value yt plus k minus our prediction y hat t plus k given t, which we just calculated to be phi to the k power yt. So what to do about this? Well, first we'll take yt plus k and see if we write that first as phi t plus k minus 1 plus epsilon t plus k. That was what we did just before a couple of times. Now we'll take this here and expand that in the same fashion. And then if we repeat, and then if we then multiply in here, we get phi squared yt plus k minus 2 plus, then comes a phi on the epsilon t plus k minus 1, and we have to keep the epsilon t plus k as well. And we can repeat doing this for yt plus k minus 2, insert it like this, multiply in, and then we get something with phi to the third power, and then we have on the yt plus k minus 3, note the exponent there and how far you go backwards in time. Likewise, you have phi to the second power, epsilon t plus k minus 2, phi to the first power, epsilon t plus k minus 1, and then there's nothing, it's just the epsilon t plus k. And given that we've done this there, we can go to the k step to get this down here. Because what we wanted to get down to is something with yt. Luckily, it does actually contain phi to the k power yt, which was our prediction. But then we have all the epsilons out here. So if you look at the variance here, what we look at, well, these epsilons are independent. So each of these terms gives a contribution. And we take a constant times a stochastic variable, and you want to look at the variance of that, it's the constant square times the variance of the stochastic variable, which is sigma epsilon square here. So we need to take this one square times sigma epsilon square plus and so forth. It's written here, the variance of this sum here. We can see that we need to take each of the multipliers here square. So it's phi to the 2 times k minus 1 power, and then phi to the 2 times k minus 2 power, down to phi to the second power, and then a 1, all times sigma epsilon square. And we can do the usual prediction interval, typically 95%. And here, since we assume that everything is Gaussian, we have not estimated our parameters, we'll use the normal distribution or standard normal as our reference for finding quantiles, and just multiply with the standard deviation as we do here. So the next step, this was for an AR1 model. That was the easy one. If we then go for an ARMA P, Q model, life is a little bit more difficult. Let's just say that K is greater than the maximum of P and Q, just as a starting point. So we have the process defined here with all, so that's yt plus k, and then everything is just plus k as the time point relative to t. if we take the conditional expectation everywhere and then move all the y related terms that are not yt plus k to the right hand side, we get this note that here we have negative signs as we have been positive here. Now we have to look at all this. We don't have epsilons yet. We know that if they are out in the future, the expectation is 0, but if they're in the past, we can actually calculate it. And we don't have the future predictions either, so what we will do is that we make a recursive method, first predicting yt plus 1 given t, and then we use that to progress. For the epsilons here, what we need to do is to invert the process like this, so that we have epsilon t as a function of the previous y's, and it is invertible, then these pi weights go sufficiently fast to 0, and we only need, you can say, some element in that term, some, to get a good enough estimate of epsilon t. So that was the prediction. Of course, we also need to get a variance of the prediction error. Here we want to have the process written on psi form. So to make a k-step prediction, well, we have the sum of psi k, epsilon t, blah, 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 here all the way down. And the prediction error is the usual definition, yt plus k minus y hat t plus k given t. Oops. The definition here is that it's only the future epsilons that are unknown. All the up to epsilon t are known from what we did on the previous slide. So we have to look at the contribution from all the future epsilons. So what we will end up having is a 1 multiplier here on sigma epsilon square, and then we have phi 1 square and so forth down to psi k minus 1 square. This is exactly the same thing we did for the AR1 model. We just had a structure of the psi coefficients here, which we just go back a few slides. You have the weights up here, some powers of phi. So we have a little bit more complex structure here, but we only have one parameter here, where in the psi here, each of these can be calculated from the previous setting. So that is the prediction error. I'll just round off with a quick example of predictions and bond prices. We have some time series here that we assume that we observed. We specified this model. Consider the class. Well, you have b to the second power here, and you have one order of differencing. So this is an ARIMA model where the p equals 2, d equals 1, and there's no moving average part. So it's an ARIMA 2, 1, 0 model. And you should just subtract the global mean value at first before doing anything. So given the last 6 prices, you're asked to predict the price in 2 days from now. First thing to do is to multiply the AR part out to get phi and b nabla defined like this. And this is when you multiply out to get a third order polynomial in b. Then what you need to do to get the expectation of yt hat, t plus 1 given t, well, you get it directly from up here. You have this coefficient with opposite sign on yt, opposite sign again for yt minus 1, and opposite sign for yt minus 2, because we're looking relative to yt plus 1, so that corresponds to b to the third power. We can just insert everything here and get 87.06 when we also correct it for the mean value. we are asked to do the two-step prediction, well, we'll do the same thing with the one exception that now we don't have the one before as an observation, so we'll use our estimator as we did for the AR1 model, y hat t plus 1 given t, but we do know yt and yt minus 1 down here, so this will be our prediction 2 steps ahead. Next we need to look at the variance, but here we can see that we have the order that we want. We want to look at the variance of the two-step predictor. If we do as we did for the AR process before, we have the epsilon t plus 2 plus the coefficient of the AR1 part here on epsilon t plus 1. And as always, we take the constant outside here and we square that when we get into the variances, and we get an estimate at a 0.499 square, and we get a prediction interval in this case from 86.05 to 88.01. So what is left now is the highlights from today. We have talked about stochastic processes. In general, it's a random variable. If you look at a sample at one point in time, typically we'll have a time series as in one realization of that. We discussed stationarity, meaning that the distribution is invariant to changes in time. Typically we'll just look up at the second order moment representation, including the autocovariance, so which will only depend on the time difference if the process is stationary. Likewise, the mean value is a constant across. And we looked at the moving average, autoregressive, and ARMA processes, and the ANU processes that we will get back to in the next few weeks, and trying to describe both seasonal and non-stationary processes. And we'll also get into how to estimate, how to identify these models next week. And for doing the predictions, we are back where we started with the conditional expectation, and that's something that we're going to do a lot next week. So I think that's all for now. Bye bye.